All right. Good day, everyone. Welcome to this video lecture for other wireless networks. This is module 25. Okay. So this module is supposedly under the local area networks module, wherein there we discussed wired LANs, where we talked about IEEE 802.3 and Ethernet. And then we also talked about wireless network, in particular the IEEE 802.11 set of standards. So today we're going to talk about other wireless networks, in particular cellular networks and satellite networks. So let's start with cellular networks. As you know, cellular networks are widely in use today, and basically because of the cellular phone or the mobile phone, and everyone has his or her own cellular phone connected to a provider, let's say Globe, Smart, Talk and Text. Now, let's discuss how cellular networks operate at a high-level view. The design of cellular network is basically due to the main goal is to provide communication between two moving units called the mobile stations. Basically, you have cellular phones, tablets, or between one mobile unit and one stationary unit called the land unit. So during the early days, we have landlines or the normal telephone line with a telephone with handsets, and then along came cellular phones, wherein you can call using cellular phone, a landline phone. So these are the two configurations that are typical with the introduction of cellular networks. A service provider must be able to locate and track the caller, assign a channel to the call, and transfer the channel from the base station to base station as the caller moves out of range. So there is a service provider which provides the functionality for tracking a caller and then assigning it to a communication channel. So again, the objective of this is mobility, meaning you have a cellular phone, mobile device. Right? So you move around the different areas, and while making a call, you should still be able to continue communicating with other mobile station or a land unit. To enable tracking, cellular service area is divided into small regions called cells. So that's why it's called cellular networking. So a geographical area is divided into smaller regions called cells, which you will see later. And each cell has an antenna powered by a network station called the base station, or basically what we call it today as cell towers. And each base station is controlled by a switching office called a mobile switching center to coordinate the communication between all base stations and the telephone central office. The size of the cell is not fixed, but it's basically has a radius of 1 to 12 miles. The cell size is optimized to prevent interference of adjacent cell signals, as you will see later. And the transmission power of each cell is kept low to prevent interfering with the signal. So here is a typical general architecture of a cellular network. You have here a stationary phone or a landline. This stationary phone is connected to the public switch telephone network or PSTN. Then here you have a cell. This particular cell is within or has a base station at the center of it. And then you have mobile stations within this particular cell. So, and then you have the mobile switching center here. And this can be connected to other cells also. But this is a typical scenario. Okay. So I have some visualization here of cellular communication. So as you can see, we have a mobile station here. So we can assume that we have base stations here, and this is the coverage area of the base station. We can add a mobile station here. So currently, if the mobile station is somewhere here, there is no signal, so it cannot receive any calls. But if it is within a particular cell, so let's say in this case, we have base station 5, and then you have the cell here, then we can simulate a call. So the call will go to the mobile switching center, and then it will forward it to the corresponding mobile station. Now let's look at the operation of cellular networks. There is a frequency reuse principle used in cellular networks. The number of cells define the pattern. Cells with the same number in a pattern can use the same set of frequencies. So the idea here is, let's say you have this particular configuration wherein you have a reuse factor of 4. So in this configuration, this cell, for example, will use a different frequency. This one will use a different, 2 here will use a different frequency, 3 here will use a different frequency, and 4 here will use a different frequency. So the objective of that is to minimize the interference among the cells by using different frequencies. So here we have a reuse factor of 4. Now we can increase that, can have a reuse factor of 7. As you can see, this will be the configuration. So I have another visualization for that, for this cellular frequency reuse. So here we have, let's say, these cells, right? And let's say we have 4, right? The reuse factor of 4, n equals 4. So we're going to use frequency, this color for frequency 1, this one for frequency 2, this one for frequency 3, and this one for frequency 4. Now, if we regenerate the network, okay, and then clear it up, okay, let's say I put in a cell now, a cell for a mobile station here. So currently the color is this one. So this is frequency 4. Now, if I put in a cell mobile station here, so it will use a different frequency. As you can see, the frequency being used is frequency 3 based on the color. And then this one here will use a different frequency, frequency 2. And lastly, if you're going to guess it right, this will be frequency 1, this which will have this color shown here. Right? Now, if I put in a station here, what do you think is the frequency that will be used here? Now, it cannot use frequency 1 because this is directly adjacent here. And it cannot use frequency 2. So it can either use this one, frequency 4, or frequency 3. So if I put in a station here, it will use frequency tree. So you get the idea of having different frequencies for neighboring cells and the parameter frequency reuse factor. So how is transmitting done in cellular networks? So what happens is that the caller will enter a code, basically a mobile number, and the mobile station will scan the band based on the type of cellular network, seeking a setup channel with a strong signal and sends the phone number to the closest base station using the channel. So you have the cell tower, it scans for the nearest cell tower, and then it initiates the setup channel. The base station relays the mobile number to the mobile switching center, and the mobile switching center sends the data to the telephone central office. And if the called party is available, the mobile switching center assigns an unused voice channel to the call, and the connection is established. So there is a connection establishment process. So when you dial a number, it will ring, and if the other end is available, if the call gets accepted, then connection is established. So receiving, telephone central office sends the number to the MSC, and the MSC searches for the location of the mobile station by sending query signals to each cell called paging. So it will try to search for the mobile station. Once the mobile station is found, the MSC transmits a ringing signal, and then when the mobile station answers, a voice channel is assigned to the call, allowing voice communication to begin. That's the receiving part. Now, during conversation, for example, you are in a car, the mobile station may move from one cell to another, and thus the signal may become weak because you have at the center of the cell the base station. As you move farther away from the base station, the signal, of course, will deteriorate because of attenuation. So what happens is that the MSC monitors the signal level every few seconds. And if the signal is weak, the MSC finds a new cell, then transfer the call to the new channel. So there are two types. This is called the handoff process. We can have what we call a hard handoff, wherein the mobile station only communicates with one base station. And we also have what we call a soft handoff, wherein the mobile station can communicate to both base stations, both the old and the new cells, where it is within range. So I have again here a last visualization for cellular network, which is the handoff process. So as you can see here, you have the mobile switching center here, and you have cells here with base station 1, base station 2, and base station 3. Now, this is the path that the mobile station will be going through. So if we start the simulation, so what happens here is this mobile station, while moving within the range of this cell controlled by this base station, it will remain connected to this station. As it moves out, it will the handoff process will take effect. Okay, so as you can see, the mobile station still connected to the base station 1. Then as it exits, it should be connected to base station 2. As you can see here, so it turned, this is the connection now. And then as it moves along again, okay, it will be connected to this base station 3. So this is basically what you call the handoff process. That's one of the feature or the advantages of cellular networks. You can maintain the call Of course, there will be some small delays as you transition from one base station to another. So roaming is another feature of cellular networks wherein, let's say you go to a different country and you still would like to use the cellular network. So what happens is that neighboring service providers can provide extended coverage through a roaming contract, meaning from one service provider, the they can connect to another service provider as long as the two providers have contracts. So let's look at the different types of cellular networks. The first one is what you call first generation or 1G network. So probably it was in the Philippines. I got my cell phone when I was in college, maybe second year college. So it still uses the 1G technology. So the first standard or technology is 1G, first generation, is advanced, called AMPS, Advanced Mobile Phone System, which was used in North America, and it uses frequency division multiple access. It is designed for voice communication using analog signals and uses the 800 megahertz ISM band. So it separates the communication channel into two. It has the forward channel, which is from the base station to the mobile station. So this is the frequency range used. And the reverse channel, which is from the mobile station to the base station. And this is the frequency range used. Now, of course, during communication, there will be some control messages. So 21 channels are used for control. And in AMPS, the frequency reuse factor is 7. So as you can see here, you have the forward communication, which is base to mobile. Okay. And then you have the reverse communication, which is mobile to base. Okay. And you have each band is 25 megahertz and made of 832 30 kilohertz analog channel, which is basically used for voice communication. So for the low-level mechanism, so AMPS uses frequency modulation, which is for the voice channel, and frequency shift keying for control channel. So these are analog techniques. So for example, you have here 832 channels, right? And of course, as we know in the lecture, that a the frequency range used by voice data is 3 to 4 kilohertz, right? And it will be modulated using frequency modulation, and will generate 30 kilohertz analog signals. And then you have frequency division multiple access to allow this communication to happen. So in a way, in a base station, they can have, let's say, 832 callers at the same time, because each will have its own channel. Now, here comes the second generation cellular networks. So it's called 2G, so designed for digitized voice communication. So instead of analog, you have digitized, so digital. So we have different systems. We have D-amps, GSM, and IS-95. For the D-amp, so it's basically amps, but instead of using analog transmission, it uses digitized or digital transmission. As you can see here, the input voice is digitized. Compare this to the original amps design, wherein it uses frequency modulation to create a 30 kilohertz analog signal. Here, it has a digitizer that converts the 30 kilohertz analog data to 7.95 kbps digital or digitized data. And then in order to do multiplexing, so here you have, it uses TDMA, time division, multiple access, and you have the different calls here. Okay, so you have 48.6 kbps, and then from there, it converts that to this input here will be encoded using QPSK, quadrature phase shift keying, okay, to convert this to analog 30 kilohertz signal. So if you can see the information, if you compare AMPS from DAMPS, so still have 30 kilohertz analog signal. So you have 30 kilohertz, and it uses frequency division, multiple access in the same manner here. So the main difference between amps and deamps is the digitization step that is happening here. Now in the Philippines, I think I've used this GSM. Okay, so GSM stands for Global. It's a second generation cellular network. GSM stands for Global System for Mobile Communication, and it is Europe-based, and the reuse factor is 3. So as you can see, you have the forward band and the reverse band here, each with 124 channels. Okay, and each channel, so the band is 25 megahertz, and each channel is 200 kilohertz. So you have 124 channels, and this is the range of frequencies used in GSM. So the way GSM works, again, you have the, let's say, your calling. So you have your voice data. It will be digitized to generate 13 kbps digital data. And then it uses time division, multiple access. If you compare this to DAM, so it also uses TDMA. So time division, multiple access, and this one will have what we call multi-frames. Okay, so you group a grouping of frames here within this duration, and then it will create 280.8 kbps, and it will generate this, I forgot the GMSK, but another encoding technique, shift keying, okay, and then FDMA, where each channel here will be 200 kilohertz. And the band, entire band is 25 megahertz band. There are some overhead when using GSM. So let's say you have 65 bits of user data. You add additional control bits for that for error detection. And then again, you have multi-frames here, multiple frames. So there are excess bits that are added for error control. The next generation of cellular networks are what we call 3G, third generation. So 3G, the goal is to provide both digital data and voice communication. So up until 2G, the priority is for voice communication and digitized voice communication. But in 3G, digital data and voice communication are priorities. It started in 1992, and it uses the internet. It has a standard called Internet Mobile Communication, or 2000, or IMT 2000. So what is this third generation or IMT, in particular IMT 2000 blueprint? So the objectives are the following, basically. The voice quality should be comparable to that of the existing PSTN. So you have digital, right? So the voice quality should be comparable to that of existing landlines. The data rate of 144 kbps for moving car and 384 kbps for pedestrians and 2 Mbps for office. So these are the data rates, because again, the third generation would support data communication in addition to voice communication. And it should also support for packet switch and circuit switch data services. Recall our discussion about switching, where we talked about circuit switching and packet switching. And the band will be 2 gigahertz, which is way bigger than those in 2G. And the bandwidth is of each channel is 2 megahertz. And since this is cellular communication, one priority is that it should interface to the internet, which was also developing during that time. So these are the radio interfaces in the IMT 2000. So you have CDMA, CDMA, TDMA. So these are the different radio interfaces that are supported by IMT 2000. Now here comes 4G, right? So 4G, I think this is still what we have today, what you are using in your cell phone. So 4G, right? So it is the objectives are the following. It should be an spectrally efficient system, high network capacity. For a moving car, there should be 100 Mbps. So you probably experienced this. I don't know if you really can get 100 Mbps while riding on a van and then accessing some data. And 1 Gbps for stationary users. There should be a smooth handoff across heterogeneous networks, seamless connectivity, and global roaming. So all IP here is Internet Protocol and packet switch network. So this is basically, in a way, a modern network, a modern cellular network type. So what are the features of 4G? So if you look at your cell phone and you look at the type of network that your cell phone is connecting. So most cell phones can connect to 3G, 4G, and 5G. So if you have a newer cell phone, you can connect 5G, but older cell phones can connect to 4G or 3G network. So the signal indicator will tell you whether you are connecting to a 4G network or a 3G network. So access scheme, so it uses orthogonal frequency division multiple access, FDMA or CDMA. Modulation, you have 64 quadrature amplitude modulation for LTE. It uses software-defined radio, and it uses the MIMO for antenna technology. So the latest, or I think this is not the latest anymore, but this is not yet widely deployed, but it's supposedly a newer generation. In the Philippines, I think some of the providers offer services for 5G. So it uses orthogonal FDM encoding, and it uses millimeter waves. Okay? It has limited range, can be blocked by materials like walls and windows. So since it uses millimeter wave, so it cannot penetrate walls. So the signal will be affected if you have a lot of buildings. In some cases, some studies, although not yet really established, is that it can cause some health concerns. It can use low, medium, or high frequency bands, shown here. So you have 24 to 47 gigahertz, and can achieve a peak at 20 Gbps data rate. So, but again, I have some friends, colleagues who said that, yeah, 5G is fast, but if you are in an open area, but if you are in a crowded area, 5G is not that good. And another promise of 5G is the support for what we call the Internet of Things, wherein we have different devices can connect directly to the internet via 5G. And it's useful for urban areas. So here is an example illustration. I just looked at some of the statistics related to 5G in Los Baños. There's a link here. Copy hyperlink location. Let's see. So this site here will tell you the coverage. So, as you can see here, let's enlarge this. Okay, so 5G, 4G plus, 4G, 3G, 2G, and 1G. So let's say, let's go to Batong Malaki. Okay. So you can see that the signal here is mostly 4G, 4G plus. And here you have 5G somewhere here near Anos. Right. So you have here the signal, the type of network technology, network generation being used. Okay, so that ends our discussion on cellular networks. So we move on now to the other type of wireless network, which we call the satellite networks. So what are satellites? So it's a combination of satellite networks. So it's a combination of nodes, artificial satellites, earth stations, and end user terminals or phones. It's similar to cellular networks wherein the earth is divided into cells. And the advantage of using satellite networks, it is for underdeveloped regions wherein there is no, let's say, wired infrastructure, no fiber optic cables, no wired network. So satellite networks are essential or will be very useful in underdeveloped regions because it's purely wireless and uses satellites. So some terms, a period is the time required for a satellite to make a complete trip around the Earth. So the period is equal to 1 over 100 times the distance, that's 1.5. And then the Earth radius is 6,378 kilometers. So these are the possible orbits of a satellite. Now, footprint. What is a footprint? So, a footprint is the specific area where the signal is aimed and the signal strength is maximum. So it's called the footprint. And process microwaves with bidirectional antennas are line of sight, basically. Right? So it's called the footprint. And for the frequency bands, we have different bands here. You have L, S, C, Ku, and Ka. And these are the frequency used for the downlink, the uplink, and the total bandwidth. So these are the bands used by the satellites. Now there are three satellite categories based on how far they are from the Earth. So the first one are called geostationary Earth orbit or GEO. So they are 35,786 kilometers above. So these are typical satellite networks. And the next one is medium Earth orbit or MEO. So 5,000 to 15,000 kilometers. Sample views of this are for GPS, Global Positioning System. And then you have LEO or low Earth orbit, so which is below 2,000 kilometers. Now, this is the illustration of that. So you have the Earth's surface here, and then you have LEO here, and then you have the MEO here, and then you have the GEO here. For the GEO, so they basically are far away. So they are the typical satellites that we have. Right? For the MEO, this is used, it's basically for global positioning system GPS. Most mobile devices today can process GPS signals. So it can receive signals from GPS satellites that allows you to pinpoint your location. So we have what we call trilateration. which allows the given three signals, three satellite positions. You will be a position given three satellite information. A particular location can be identified on Earth. So that's basically how uh, GPS works. So you can use it for finding directions, for travel, etc. So Leo, the altitude is between 500 to 2,000 kilometers, and the speed is 20,000 to 25,000 kilometers per hour. And the diameter of the footprint where the signal is strongest is 8,000 kilometers. It uses a constellation of satellites connected with each other through inter-satellite links or ISL. What happens then is that the mobile system connects through a user mobile link. And then the satellite communicate with Earth station using a gateway link. So this is an example of that. So you have this is the footprint, right? So you have the UML. Again, UML is user mobile link, right? And then you have the GWL here, which is the gateway link, right? And then you have the inter-satellite link, okay, between the satellite. So this is how uh, uh, this satellite network LEO works. And the best example that we have today, which is commercially available, is the Starlink technology. So Starlink is the world's first and largest satellite constellation using a low Earth orbit to deliver broadband internet capable of supporting streaming, online gaming, video calls, and more. Okay, so it uses low Earth orbit. It's a low Earth orbit. Starlink uses low Earth orbit satellites. So I have here a link for to view the satellite constellation of Starlink. No, this one. So copy this link. So here is can view the constellation of the different satellites. You can see there are a lot of satellites. So this company is owned by Elon Musk. And you can see here that you have a tracker that tells you, okay, where the satellites are, right? And yes, so you need to buy an antenna to be able to receive signals from the satellites owned by Starlink. So you can see there's a lot of satellites if you zoom out, right, all over the world. Very interesting technology. Okay, so that ends our discussion on other wireless networks.